Hey, good morning, you guys. We'll start in just a minute. I'll wait just a few seconds, but up on the board, I have what we're going to start on. So, all right. Well, what I want to do today with you guys is, first of all, do a bit more on those what are called internal flows. So, as engineers with fluids, we would like to understand both external flow, and we'll do external flow a little bit later on. So, if you imagine that this represented a cylinder, what jumps to my mind is on the top of on the top of one of our cars, we have some bike racks, and we have a cylinder there like that. So as the car is moving along, air is passing externally over that cylinder. Well, what's going on with that? What kind of drag do we get and things like that? It's kind of interesting thing that all that's been worked out, and we'll be going over that in that course. The contrast that we're doing right now is internal flow. So this is actually, you look at this piece of pipe right here and you think, hey, that's not that expensive, but I got it for some project that I'm doing here at home. And man, just this was actually part of a little bit longer section, but that's expensive. And as engineers, we go through and size pipe, kind of bread and butter. How big does the pipe need to be for a certain internal flow? And that's what we're working on right now. So two internal flows that we would like you to know something about. One is this steady state laminar viscous flow between two plates. So 6.9, we went over that last time. A great way to think about it is maybe like channel flow. It is an internal flow, so we're going to have some sort of flow going in between the two plates, so it's internal flow. And a way of thinking about this could be like a channel, a long channel that its cross section is a U here like this, and it's carrying some sort of fluid that's coming, say, towards us through that channel. And so we would be looking overhead, we would be looking at this channel down here and trying to visualize what's going on with flow in that case. So here's some things that we're supposed to be comfortable with about that type of flow. So first of all, it's steady state, so that if there's a certain GPM entering here, there's a certain GPM going out. It's laminar, so that means layered flow. We'd like to know it's layered flow. It's viscous. That means, for example, that we couldn't apply the Bernoulli equation, say going from 0.1 to 0.2, because viscosity plays some role in all this. What are some things that we're supposed to know? So let me just get those up there. This we had before. What does the flow profile look like? So if we went, I want to add this to your drawing, if we went to any point in the flow and we're looking down on it, if we compared, say, the speed of the fluid here to the speed of the fluid there to the speed of the fluid in the middle, what would that look like? Okay. And I could try to trick you and say, okay, look, hey, it's steady state. How do these three speeds actually end up comparing? And so someone might say, oh, they should all be the same. As this is 3 feet per second, this should be 3 feet per second, that should be 3 feet per second. The reason that's not right is this idea right here, combined with the no slip condition. So there needs to be zero velocity at the wall because of the no slip, zero velocity at the wall, no slip. And we end up getting more speed in the middle, and it turns out that the profile is parabolic. So a term you'll see if you do stuff in fluids, hey, we get a parabolic profile. That means the way it's usually drawn as we did last time, more speed in the middle, zero speed at the walls, so we get a parabolic profile. Okay, the next thing is that we're supposed to understand is, what if we had a pressure gauge right here? And what if we had a pressure gauge right here? Okay. Let me try to fool you and make you believe that the pressures would be the same. If I called this 1, and this is P1, and I called this P2, the pressures would be the same. So please don't write this down, but here's my attempt to fool you. You're not writing this down. You're just thinking, no, I'm not going to be fooled by Professor Romani. That's no way. Okay, so here we go. In this equation right here, V is the average speed. So if this was 1 right here and this was 2 right here and it was steady flow, it would got to be true that this is equal to that right there. Okay, so again, V1 is the average flow, say right here, and V2 is the average flow right there. It's steady, so if there's 10 GPMs in, there must be 10 GPMs out. These are the same, so I can cross these out, and hey, it's looking like this. All right, so let me pause for a second, and if you can see if you can find the key word on the board that says that that equation is not true for this situation. Okay, and once again, the key word on the board is this word right here. There is viscosity, okay? And viscosity ends up meaning if viscous effects are significant, we cannot use this equation here, and this is the Bernoulli equation. So in a case like this, hey, we've got flow between some sort of channel, well, relatively speaking, the channel is narrow, can't use that equation. So it's going to be true that P2 is not going to be equal to P1, and in fact, what is P2 going to be like? As we go down there, there's friction. Friction takes away energy. It's not taking away elevation energy. It's not taking away kinetic energy. It's taking away pressure energy. So P2 is going to be less than P1. And a great way to think about that is we are going to get pressure drop. And there's one more thing that I'd like you to be able to understand conceptually. All right, so to understand what I'd like you to do next to work on understanding what's going on there is to do a drawing of an element of fluid that's in there, okay? So you don't need to put this in there. You don't need to put this in your drawing, but let's just imagine that we're taking a look at some fluid that's in that channel. So it's in that channel, it's between 2 plates. Some rectangle of fluid. Okay, so that rectangle of fluid, what we're going to do is I'm going to take it, I'm going to draw it down like here, like this. I'm going to make it a little bit longer maybe to indicate that it's in the channel. Okay, and we're going to imagine that even though this Y direction seems up and down, we're going to imagine that this is moving horizontally like this, where Y is just the distance from a center line. Okay, what I'd like you to brainstorm and is think at each of the edges. Can you think of a force that's acting at each of those edges? Okay, and what we're going to do is we're going to attach the force. We're going to draw arrows at each of those 4 spots. So here, up, down, left, right. 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 I want to pause for a second, let you think about it, and I'll give you a force in just a minute. Okay, so let's get, this did not go so badly on test 1. You may look at your result for the nozzle problem and say, I was kind of shaky on that. And yeah, there was some shakiness on that, but there was also some really good stuff. And regardless, I felt like there was progress. Okay, this element right here, okay, it's moving to the right, okay? It's moving to the right. And it's moving to the right essentially at a constant speed. Why constant speed? Steady state, okay? I'm talking about overall average speed. Okay, for many of us, we would think, hey, something moving to the right at constant speed, like a block in physics, that means there's no forces on it because it's a constant speed. It's neither speeding up nor slowing down, okay? But that's not really true. Bear with me for just a second here. You know, I experienced that yesterday. I went out for a bike ride with my son, who's 20 and kind of in great shape compared to me, and I tried to keep up with him. And I tried to keep going. I was trying to keep up with him at about 15 miles per hour. Okay, it took a lot of force for me to go 15 miles per hour. And what was going on there was a drag going back on me. and I need to compensate by creating a forward force on the bike. So there can be something going at constant speed and there would be balanced forces, okay? So first of all, what would create, say, an analogy, a backwards force, kind of like drag in this case? Well, that's friction against the wall. Remember this stuff right here? That fluid right there is not moving. The fluid above it is moving, and that's layered flow. So layered flow is just layers that are moving like this, one on top of the other. This layer is moving relative to that layer right there, and there's friction. So we're going to have if for this bit of element fluid right here down at the bottom, we're going to have a frictional force backwards, okay? But friction in fluids is oftentimes termed shear. So there's nothing wrong about calling this friction, but we could call this a shear forwards backwards. Okay, see if you can get the other three. Just give you 30 seconds, see if you can think, what would be the other three forces there? I think the easiest one to do next is this force up here at the top. All right, up at the top, there's going to be, that would be correspond up here like this. That's at the wall, so there would be shear as well. Okay. All right. And so if you think about it, no need to write this down, but if I just did an overall of that block, well, there's shear backwards. There's shear backwards. What keeps it going forward? What keeps it going forward? And the key to think about that, to get that, is to think about those two things right there. What was I trying to say by putting these circles here? That those are pressure gauges, and there's more pressure here than pressure there. So we would actually do a pressure force here, and I liked what I saw in some people's free body diagrams on the test. Some people did P times A, so I could call this P1 times A, okay? And this backwards arrow here would be P2 times A, okay? And which arrow would be longer? I'd like you guys to think about it. Should P1A be longer or P2A be longer? And the answer is this one should be longer because there's more pressure here than there. So adding to here, adding to this, I would say there's pressure drop and shear going on. And we're supposed to understand that when flow passes internally between a passageway, there is going to be shear backwards if it's viscous, and there's going to be a pressure drop, and the pressure is necessary to drive the flow forward. Okay, a lot of good thoughts going in that. All right, hey, by the way, on this stuff here, if you want to mute at any point and say, look, I don't understand what you're saying, please do so. All right, that is the conceptual stuff we're responsible for. Hey, what about the computational stuff? All right, so this next thing is a review of what we had last time. I'll write it up on the board anyway. What does the profile look like? What does the profile look like? And that is, let's see, let me just kind of give this over here like this. That is given by the equation U at Y. So U would be how fast it's moving in the horizontal direction, and Y would be position relative to the center line. So basically the center line is right there like that. And so we get a parabolic profile, and amazingly, some people worked it out. It's actually equal to the profile involves viscosity. So the more viscous it is, the more flat the profile is, okay? And then it involves the pressure, the rate of pressure drop, which is in the book's notation, how much the pressure drops as you go in the X direction. So Y direction would be where we are in the channel relative to the walls. X would be going down there like that. And then finally, Y squared minus H squared. Okay, where H is, Y is how far away the center line, and H is the distance from the center line to the wall. So I know you have that in your notes last time. So we got that. That is, and then there's one more equation that we're responsible for. Hey, we talked about shear. What is shear actually like for that fluid? Okay, and now we have our basic relationship for shear. If a almost like the definition of a fluid. If we have a fluid where one level is moving relative to another level, we get shear in between those two layers. And that could also be true if again, no need to write this down. if a level is, or a layer is moving relative to a wall. So, and the relationship we get is that the shear at any point of y in a fluid, if y is representing, in this case, right, with this sort of notation, is proportional to the viscosity, and you multiply it by the rate at which the speed changes with respect to y. Okay, so that is old news, but I want you to know, know that that applies to this situation. Okay, let me pause for just a second and give you a second to write that stuff down. I need to erase the board so we can get an example up there. And while I'm pausing for a second, please pipe up if there are any questions. I'll talk about like what's coming up in the course later on. Right now, questions about this. Okay, I'm going to start getting the example up there. So first example of the day. Okay. So imagine this channel is 4 meters wide. That's like 12 feet wide channel. So somewhere like you're looking at water going through a channel where it's a deep channel that's flowing from one town to another, something like that. We've got water flowing. Pardon me. And with maximum speed, 1 meter per second. Okay, so that may seem like, wow, that's not very fast, 1 meter per second. But think about that. That's over 3 feet per second, and you're watching some water going through a channel, 1/1000 that's moving 3 feet. That's actually moving at a pretty good speed for water. Okay. Let me see. What else are we? What other information do we have? Bear with me for a second. Yeah, that's it. So I'm going to erase this stuff and get the questions we're going to try to work on. We are going to try to figure out the pressure drop rate, but I'll put it up there symbolically. We are going to try to figure out an equation for u at y. A function for u at y. Like if we needed to graph, what does the velocity profile look like? Okay. We are going to try to figure out the wall shear. Okay. And then finally, for D, it's something that I wouldn't write that down, but I would, just a note to myself, we're going to talk about the fluid internal shear. What's the fluid internal shear like? Okay, so let me just pause for a second and get you guys going. Hey, we only have one equation with dpdx in there right now. So it should not be hard to figure out, hey, which equation do I need to use? I'll get that up there in a second and see if we can put it together and somehow come up with a number for that. Okay, so this is a bit repetitive. We did an example like this last time. But I just want you to, again, try to visualize this situation, the information given, and figure out, okay, what could we plug in so we could actually get the PDX? This is obviously what we want to solve for. So I'll give you another second to work on it. If you know what you're doing, hey, keep going. See if you can come up with a number. I worked this out early this morning, went through it. It's supposed to be a very, very small number, a very, very small number. Okay. And by the way, we're going to do it in pascals per meter. What's the pressure drop in pascals per meter? Okay, so obviously what we want to do is we want to plug in a number here. Okay, we would like to plug in a number here. And it turns out that we actually know 3 different U's just from the situation. Okay, so I won't write this down, but it turns out we know U at 2. And I would encourage you to think about that. Hey, what if on the quiz tomorrow, and please don't stress about the quiz tomorrow, you're asked to figure out U at 2. See if you could come up with that number, like as a quick hitter, a short question. U at 2. What is U at 2 equal to? Okay, well, where is 2 actually? This is Y equals 0. This is a 4-meter wide channel. So this would be 2 meters right here like this length from the center line up to here. And then this length from the center line down to there would also be 2. So Y equals 2 would be this point right here. And that's the wall. So U at 2 would be equal to 0. Okay, well, that's looking pretty good. If we're trying to fill in numbers, we could put in the number 0 there like that and solve for dpdx. But that's not going to get us what we want actually, because that might be a little bit difficult to do mathematically. It turns out we also know U at 0. I'll change pins on you. Sorry about that. Yeah, we also know U at 0. That's U at the center line. That's where it's a maximum. U at 0 is equal to 1 meter per second. Okay, so again, we would like you to understand there's a parabolic profile, and that means that the velocity maximizes at the center line. So we have this thing right here, viscosity we can look up. Okay, at the center line, what is Y? Y is equal to 0. Okay, and what is H in this case? H in this case stands for the distance from the center line to the wall. So in this case, H is equal to 2 meters. H equals 2 meters. So we're going to fill in 1 here, viscosity of water here, 0 here, and 2 there, and go ahead and solve. And I'll be cranking it on the board, threw it on the board. Please stop me if you see any mistakes. I like to do the algebra first. So solving for dpdx. Again, at any point you see a mistake or have a question, please let me know. Going to my tables. Unless otherwise stated, if you have a fluid that's in the tables, you can assume that you can pull values from those tables. So viscosity is 1.12 times 10 to the negative third. U at 0 is 1. And this is negative 4, because 2 squared is negative 4. And we're going to get some incredibly small number. Let me try it out myself. Okay, you could write it with scientific notation, but to make a point, I'm actually going to write it out. Okay, that's almost good, what I got there, 0.00056. Couple problems with it. I'm missing a negative. Okay. So, much better now. So what is this saying? dpdx stands for the rate the pressure changes as I move in the positive x direction. And it's assumed that the positive x direction is that way. And so as the water goes down this way like that, it's losing pressure. it's losing pressure. Okay, how about units? Okay, I claimed we wanted it in pascals per meter, and that should make sense. That would stand for how much pressure drop there is per meter length we go in that way, all right? And it turns out you can get to those units by using the units that are given in the book. But let me just show you another thing to consider. I'll just do the units over here like this in a different color. This bottom right here is meter squared. So I'm just going to go through the units. The bottom is meter squared. Here, this is viscosity. And viscosity is, hopefully you can see this, is Newton seconds per meter squared. And I kind of like this in some other books. Sometimes they write viscosity in a unit form by combining a Newton per meter squared. A Newton per meter squared is a Pascal. So viscosity could also be written as a Pascal second. You make a note of that. That sometimes is a very useful thing to think about. So I have viscosity here, which is Pascal seconds. Okay. And then I have U, which is meters per second. Okay. And then it works out pretty nicely. The seconds go away. I have a meter and a meter squared here, so I have a Pascal per meter. All right. All right, so there's our first example of the day. There's our answer. Okay. When I first took this stuff, I might have said, okay, well, look, I'm just not going to worry about pressure drop when I'm doing it in design. I mean, that looks like hardly anything. That's hardly any pressure. Remember, like if this were a channel going from one town to another that maybe was like 10,000 meters, well, the pressure drop would be significant. So I'm going to multiply that number by 10,000. Okay. And I get 5.6 pascals. So that would mean in this long channel, again, I need to write this down, in this long channel, I would need more pressure here than here in order to get flow. I would need higher pressure here. And I need something to generate that pressure if I'm an engineer and doing the design. And of course, so often it's some sort of pumping mechanism that actually pressurizes the water here. So it has enough pressure to make it down that channel at the flow rate we want. In general, with channels and pipes, these pressure drop numbers are small, but they add up over any significant length that we're doing design for. Okay, good. So I'm going to leave this number on the board and let's take a look at B. Let me remind you what we're trying to get at B. We're trying to say, what if for some reason we actually want to be able to graph the velocity profile? Well, that would be coming up with this equation right here. What we're going to do is we're going to actually try to come up with an equation with every number filled in except for y. So you're going to try to fill in numbers to this equation and see how it works out. Okay, so I'm going to go ahead and give it a shot. So we're on part B. I'm going to erase some stuff and give it a shot. Okay, hopefully you're making some progress on your own. Okay, the way I would think about it is a good way to think about it is we have numbers for all this stuff right here. We could actually put this stuff into our calculator and come up with a number right here and be careful about units. And then we would have a single number here. I'm just going to call it 7. Suppose that would be 7. Then my function would look like this: u at y. Hang on a second. Sorry about that pen. Yeah. Again, you're not writing this down. U at y is equal to 7 times y squared. And remember, h is equal to 4, so it'd be y squared. H is equal to 2, so it'd be y squared minus 4. Well, hey, that's a function you could graph. That's nice and easy to work with. So how am I going to get this number here? I'm going to do a quick computation and see if I can figure out what this turns out to be as both a number and units. So let's give that a shot. I forget, I'm missing one number over here in my computation. I needed that 2. So I needed that 2. Okay, so there we go. So now I can crank through that. So this is 2 times 1.12 times 10 to the negative third. And I'm going to think about it a little bit. Okay, so let me crank through that. So first of all, we're just going to try to get a number on our calculator. Okay, so I'll pause for just a second and see if there's any objections or concerns. And while you guys think about it a little bit, I'm gonna do that again on my calculator. My calculator is giving me 0.25. I go through it, 0.25. Okay, looks good to me. We'll be able to check it in a little bit. All right, and then how about units for this? The pressure drop is pascals per meter. The viscosity we can do is pascal seconds. So the pascals are going to cancel out, and we're going to have units with a meter and a second in the denominator. Kind of weird. Okay, but let's go ahead and finish it off. That was a preliminary step. Okay, and then the next thing, now I don't need this anymore. The next thing we're going to do is we're going to try to write that function u at y. So what does u at y look like? We're going to try to finish this off. So all this stuff right here in the, pardon me, all this stuff in the blue is 0.25. Okay, and then in the brackets here, I've got y squared minus, and h was 2. So that would be 2 squared is 4. Okay, and what kind of units does this bracket have? Well, h is in meters, so this would be meters squared. So taking a look at the units, this is 1 over meter seconds. And then this bracket right here is meters squared. And you guys can do that yourself. I mean, that's going to simplify really nicely.
Is it negative?
Okay, and hey, a minus for me. I'm missing one thing in my function right there that messes it up. One important thing, okay? And it comes from this thing right here. The pdx was negative, so I really should have put a negative right here like this. Okay, the pdx over 2 mu is negative, so this would be negative 0.25. Hey, and that would be 100%. That would be a good answer. Hey, what we might want to do, though, if we were just trying to simplify it, is we could multiply through. And so negative 0.25 times negative 4 is 1. And hopefully you can see that our function is going to be equal to, just do it using the distributive property. I'm going to get 1, okay, minus 0.25 squared. By the way, this is more complicated that we're going to see on Tuesday. Homework number 7. Hopefully you've got to start on it. The stuff that we have on there does involve these equations, but it's a little bit more basic. What I'm trying to do here is see that the math reflects our physical understanding of what's going on. And let's take a look at that and see if that's right. What I would like you guys to do just mentally, you don't need to write anything down. By the way, should add something to it. This function right here gives us meters per second. Okay. Hey, just mentally put 0 in there. See what you get. And does it make sense? Did we do this right? Okay, if I put 0 in here, I get 1 minus 0.25 times 0, I get 1, and I get u at 0 is equal to 1. And notice that that's what we have written on the board, actually. That tells us that the center line velocity, y equals 0 is the center line. The center line is 1 meters per second. Okay, hey, let's check the wall. Let's check the wall. So what you want to do to check the wall is put 2 in there. All right, So if I put 2 in there, I get 1 minus 0.25 times 4, and I'm getting that u at 2 is equal to 0, and that's what we want. When we get up here at this wall, the velocity is 0, and notice that if you were to graph this function as a parabola. Okay, really good, really good. I'm going to leave that up there, and let's go on to part C. Part C is, hey, what kind of shear are we talking about? And that might be a way of thinking like, hey, what kind of friction are we talking about? Because as you remember earlier, I did a rectangle of that fluid, and we said at the wall, there is shear going backwards. All right, so challenge yourself and then see if you can figure out what the shear at the wall is. It's going to involve using this equation right here like this. It's also going to involve that equation there. So I'll get going in just a minute, but see if you can challenge yourself to make progress on that yourself. How are we going to use this equation and this equation to figure out the shear at the wall? Okay, well, here we go. This stands for the viscosity of the water. This is the rate at which U is changing at any point we're interested in. So if we were trying to figure out the shear right there, that dot right there, we would figure out the rate at which the speed is changing relative to y at that point. So the deformation rate, sometimes it's called. But we're interested at the wall, so we would, maybe this wall right here, we would be interested in figuring out du dy at y equals 2. Well, let's do that. Let's go ahead and figure out du dy first. Okay. Well, the derivative of 1 is 0. The derivative of y squared is 2y. So if I got it right, I've got negative 0.5y. That's what du dy, that's in the general expression for du dy. We want to figure it out the wall, so we want to figure out du dy, and we could either do it at y equals positive 2 or y equals negative 2. Those where the walls are. I like positive numbers, so I'm going to do it at y equals 2. Okay, so negative 0.5 times 2 is 1. Okay, and that is meters per second per meter movement. So that would be meters per second per meter, or 1 over seconds. Okay. And then the last step is to now take this equation right here. So the shear at the wall is going to be equal to, by the way, I have a mistake up here. There's a negative here, so this would be negative. It's going to be equal to mu, which is 1.12 times 10 to the negative third. Okay. And that's Newton seconds per meter squared, or I'm going to write it as Pascal. No, I'm sorry, Newton per meter squared, Newton second per meter squared. Sorry about my writing. Okay, and then this is negative 1 times 1 over seconds. Okay, and then I think we could write it in scientific notation for an answer. If you did it differently yourself, no problem. 1.12 times negative 1 would be negative 1.12 times 10 to the negative third newtons per meter squared. And that's the shear of the wall. Okay, so what does the negative mean? It means on the fluid, it's a backward shear. You can think about it that way. Once again, you signed up for this course where you're supposed to compute stuff that's important to doing design. And you look at that and say, well, that's hardly anything. But remember, this is a channel and it's got a lot of wall area, particularly if it's a channel that's like from one town to another, carrying water from one town to another. Well, this is newtons of force on the fluid per meter squared of wall. The meter squared of wall might be huge. It might be something like 80,000 meters. So if I take that 1.12 times 10 to the negative third and multiply it by 80,000, Okay, I get 90 newtons of force backwards on that water due to the wall, and something has to overcome that. And that would be, once again, pumping or something like that. Okay, hey, one thing to do, I won't write this down. Okay, what about internal shear? This was wall shear. What about internal shear? Let me erase some stuff and talk about it really quickly. Again, I won't write this down, but I'm trying to do a little work on your conceptual side. So here's one wall. Here's one wall. Fluid in between. Parabolic profile. Fastest in the middle. Zero speed. So if I were to go to some point internally here like this and try to draw the water, I could draw the water like this, where we've got a layer and another layer above it. Again, don't stress about that. Those are supposed to represent layers of water, and they were actually touching each other, but I'm just sort of separating them, trying to visualize what's going on. Okay, well, this layer is going at a certain speed, and above it's going actually at a slightly bigger speed because we're in the region where it's getting faster as you go up. So there is friction between those two layers right there. And as a consequence of the rubbing, there is shear, okay? And it turns out that this one's going slower, this bottom one's going slower, so it's going to produce a shear backwards on the top one. And for the bottom one right here, the one above is going to be a shear to the right, okay? Well, if we go through any layer, it's moving at a constant speed, so the shears are actually going to balance out. Okay, that's one idea to think about. What difference does this shear make? Well, you can think about it like internal friction, and internal friction is taking away energy. And so with what's going on internally in there, there is internal shear, and that leads to friction, which takes away energy. Okay, hey, there's our first topic of the day. So that was quite a bit of information. We're going to keep going. We're going to go until about 9, 10-ish or something like that. I would encourage you maybe just to take a deep breath, stretch for a minute, and we'll get going on the second topic in just a second.
Professor?
Okay. Yeah, Thomas, please go ahead.
Do you have your sound up?
Hang on, I'm sorry, hang on. I have my volume kind of low. So Thomas, I'm sorry about that. Let me get it higher.
Oh, I was just letting you know that I don't know if you can hear us because we tried speaking up 1 or 2 times.
You tried speaking and I didn't hear you?
Yeah, and another student as well.
Okay, I'm really sorry about that. Thank you so much for raising your hand. I screwed up. I had my volume a bit low. So let me pause for a second. The questions or comments that are out there, please go ahead.
I had a question, Professor, before you erased the board.
Yeah, shoot, sorry.
No, you're all good. I was just clarifying for when you were trying to find the shear. When you did the du dy and you got negative 0.5 y, you just you found the du dy off of part B.
Yes, exactly. So many times in fluids, we can come, if we're trying to figure this thing out, this du dy, sometimes we can just figure it out from a picture. And that's what we did earlier in the semester. The picture I gave you earlier in the semester was we had one plate stationary and the other being drug along. And from this picture, we figured out du dy. Now what we're doing instead is we have a function u at y, and then we do a little calculus to do the derivative. Good question. All right, hey, other stuff out there, Thomas or anyone else? Okay, hey, let me just talk really, really briefly, and I'll try to summarize in this in an email. You know, summer is a challenge. You guys know that. I mean, I don't need to tell you that. But what I would, as far as getting things done, hey, quiz 2 tomorrow, sometime during lecture, via Canvas, short quiz based on homework number 6 and number 7. The number 6 stuff, hey, you've had that for a while. I feel like I can ask questions there fairly, which are non-trivial. Trivial is not the right word, but involves some thought. Homework number 7, I'm going to post the solutions later today. And the questions I ask there, I'm really going to make basic. It's not the case that you can't do homework number 7, but if you're thinking, wow, I need to do a really complicated problem that's going to involve a lot of thought, no, not for tomorrow. I'm going to test to see whether you got through homework number 7 and understand the basic relationships. So first of all, that's quiz 2 tomorrow. One more thing on quiz 2. As far as your grades for this semester, I do think for a few of you, I think tomorrow could be a really good day. Quiz 1, we had a huge range in how that went for people. There were some people who really struggled, so we're pretty low score-wise. But remember, for the semester, if your test 3 is better than your lowest quiz, I drop the lowest quiz. Well, as a consequence, for any of you who struggled on quiz 1, you want to make quiz 2 good so that quiz 1 is your lowest score. So again, don't stress. I think the main thing to do is just keep putting in some time. Put in some time, get homework number 7 done. I'm going to have office hours this evening. You can ask me questions on homework number 7, or if you just want to, I've had students in my previous semesters who just come to office hours and just work. And then every now and then they say, hey, I'm stuck on problem chapter 6, number 31 or something like that, and ask a question. Okay, that's the main thing that I wanted to talk about is, hey, let's make tomorrow a successful day as far as quiz 2. Okay, let's get back at it. So then, again, I'm sorry about the volume earlier. Please feel free to speak up. My mistake on that. Okay, let's get going on the next topic then. So bear with me for just a second. The next topic is, again, something that we've already done, but is a huge topic in engineering, and that is pipe flow. We would like you to be able to understand what's going on. If you size some pipe and you get some sort of fluid going through that pipe, what's going to be going on inside that pipe? What's going to be going on inside the pipe? So let's get going and work out some things about that. So first of all, some terminology that's used a lot of times. Okay, the book is going to draw a pipe like that. Okay, and they're going to put a center line on the pipe. So they're going to put a center line on the pipe like that, and the coordinate of the center line could be X or Y or Z. We're not going to worry about that for right now. Okay, but that's like a center line going through there. And then this dimension, as you go away from the center line, is going to be R. Okay, so right here, at this point right here, R is equal to 0. All right, so what are some things we get that we're supposed to say, hey, if we understand what's going on? Okay, first of all, viscous, that means there are viscous effects. There are viscous effects. Secondly, laminar, that means the flow is layered as opposed to swirling. So laminar flow means we have fluid flowing and one layer is flowing above the other, either at the same speed or a faster speed. So all this right here would be an indication we have laminar flow. We have layers of flow with some going fast, some going slow. That's opposed to turbulent flow, and turbulent flow is where we have swirling, jagged flow with the flows actually, some fluid actually crossing other fluids. So I could have fluid that's down below here and then ends up here like this, and some other fluid that's there like that. Turbulent flow versus laminar flow. We're sticking with laminar right now. Okay. Some things that we get. Do we get the no-slip condition? Absolutely. Okay. Do we get fluid moving faster in the middle than at the edge? Absolutely. And so that's sometimes said we get a parabolic profile, parabolic flow profile. Okay. And we could draw it like this, where we have a wall here like this and a wall here like that. And you might want to include that in there. That means at the middle, the fluid's going to be going fastest. And at the edges, it's going to be going 0. So you can do a drawing like that. Okay. And this is so commonly done in fluids books. Okay, sorry, my drawing's not great, but we want, and it's supposed to be a parabola like that we'd like you to recognize that. And hey, it's really, really similar to what was going on with flow between plates. Okay, another thing that we get, okay, hey, I think this is worth testing yourself for your understanding, okay? What if we took a look at some cylinder of fluid within there? Remember, it's a pipe, so its cross-section is a circle. What would the forces be like on some sort of cylinder of fluid? So why don't we just go ahead and draw it like that? This right here represents some cylinder of fluid that's in there. Okay, test yourself. See if you can add forces to those 4 drop dots. What direction are they going? And could you name them? So that's that cylinder right there like that. What would the forces of those dots be? What direction and what name? Okay, so first of all, this dot would be contacting the wall, so there would be friction between the fluid that's moving along and the fluid that's actually sticking to the wall, and as a consequence, there would be shear back like that. So there would be a shear force back there like that, and a shear force back there like that. Okay, so my intuition, just looking at this drawing, and again, I'm sorry, my writing is a little bit small. This is shear and this is shear. Okay, if this, eraser here represents that block of fluid, well, it's moving along and there's a backward force. It's going to go, it's going to come to a stop. Okay, something with backward force, usually like a car slamming on its brakes or anything like that. A tennis ball rolling on a court, because of backward force, it comes to a stop. Okay, but our description is this is not that situation. What about our description means it's not going to come to the stop? That's this term right there. It's steady state. So the flow, if there's 10 GPMs here, there must be 10 GPMs out. This must be moving at steady state. So there must be a forward force to counteract that. And over here, this fluid has pressure, and over here, this fluid has pressure. So I could call this, if I called this point 1, I could call this P1A1, and back here, P2A2. And which one's bigger? P1A1 is bigger than P2A2, and that's what causes the fluid to go along. So again, if you were to go out in industry, and I wish I had a demonstration for you, or if you were to go out on some sort of facility, and if we had a pressure gauge right here, okay, and at this point the pressure read 20 psi, and then we had another pressure gauge down here, would this one read 20 psi, more or less? If the fluid's going that way, then this pressure would be less. As the fluid goes downstream, it loses pressure. It loses pressure. So another thing that we end up getting on our list, okay, is we get shear and pressure drop. Shear, that's the word shear, I'm sorry, and pressure drop. Okay, and all this stuff, equations for this stuff, equations for shear and equations for pressure drop, this confounded people who got really, really good at fluids. Like I talked about, there's all sorts of cultures that did amazing stuff with fluids before there was much engineering going on, but they couldn't get very precise on their designs because they didn't know how to calculate the pressure drop. And that stuff is in chapter 6 and chapter 8 of the book. Okay, so for the plate case, I wanted you to know the U at Y equation, and we also did some stuff with the U and Y equation. For here, there's a ton of equations. This is section 6.9.3, but let me get that back up there. Sorry to be a bit repetitive, but this stuff's really, really important. That the volumetric flow rate, okay, in a pipe like this, okay, depends on the pressure drop rate, and that was delta P over L. The bigger the pressure drop rate we get, the bigger this pressure is here versus that pressure there, and the more steady state flow we end up getting, okay? And it also, the other stuff that's in the formula is pi r to the 4th over 8 mu. Okay. And again, I'm sorry to be a little bit repetitive, but that is the formula that we're responsible for. And let me put one more idea on this, okay? I would like you to take a look at this fraction here, and I'll write it on the board in a second, but just test yourself. Is that going to be a positive or negative number? Delta P over L. Is that going to be positive or negative? Okay, well, delta P stands for the pressure drop for our pipe. So this is a formula for a section of pipe. Hey, what's the flow through a section of pipe? Delta P is going to be negative. As you go down the pipe, it actually ends up being, P ends up being decreasing. Okay, but normally what we do is we fill in the magnitude here. You might want to write that down. That's the word magnitude. I'm sorry about that, magnitude. So we're just going to fill in a positive number. All right. There's you got that equation. Let's do an example where once again, I turn you loose and let you work for a little bit and see if you can figure it out. All right. So we're going to do water. Okay. Water is huge in our world. Okay. Yeah, and by the way, is this flow going to be laminar at the end of the semester, or maybe in the day you'll look at my work and say, wait a minute, he didn't check that very carefully. Actually, you know what? Shoot, why don't we do glycerin? Then I know I'm right. So let's do glycerin. Because glycerin is almost always laminar, okay? And we've got a flow of 100 cubic centimeters per second going through a pipe, okay? And in addition, we've got 10 meters of pipe. So 30 feet of pipe. We've got a long section of pipe, and we're going to try to do a design for it. So we're going to try to figure out the pressure drop, okay, if, and A, suppose we end up choosing a 2 centimeter diameter pipe. So 2 centimeters is about like this pipe size right here, like this, okay? And this is expensive if we did copper. So this is around 2 centimeters. Hey, if we had 10 meters of this pipe, what is the pressure drop going to be? All right. Hey, it's plug and chug. I would encourage you to do the algebra first and then see if you can substitute and get the numbers right. So a little bit of work time. I'm sorry, I'm going to step out for just 1 second, and I'll be back to work through it with you guys.
Does anyone know if that says 100 centimeters cubed per second?
Yeah, that's what I have for 100 centimeters cubed.
Yeah.
Okay. Okay. So my question is, if so, it says it's a 10-meter long pipe, and they want us to find the pressure at 2 centimeters. So is that what he's talking about? Is cutting like a portion of that pipe to only look at the 2 centimeters?
I believe the 2 centimeters is the diameter of the pipe, and it wants us to look over 10 meters.
Oh, that's a diameter. Okay.
Yeah.
I'm sorry, I stepped out for a second. Is there a question for each other or one for me?
I was just clarifying.
Okay.
Yeah.
Well, great. I'm going to start getting it up there. I hope you guys are making some progress yourself. So. Okay. You guys don't have to do it this way, but I did the algebra first myself, so I took this 8 mu L and moved it over here, and then I divided by pi r to the fourth, and I'm going to get what the pressure drop is. And I just need to be careful with what I fill in and what kind of units I get. So I'm going to erase this stuff here. I think I'm done with this. By the way, if you see anything wrong up there or questions about it, please let me know. Glycerin's like that nice, easy one where it's just there's no scientific notation. Okay, so before I get going, if you see any mistakes, let me know. But before we're going, I'm just going to try to make sure I got the units right. So I did this fraction here to make centimeters into meters because I know that a lot of the stuff is given in terms of just the standard unit. So all that stuff is going to be meters cubed. This is viscosity written again as Pascal seconds. I'm not going to require you to know that, but it is a kind of slick thing to do. Okay. Meters. Oh, I'm missing a second. Sorry, I'm missing a second because this is meters cubed per second. Pascal seconds, meters, and then the bottom is meters to the fourth. So let's see, again, sorry about my writing. Let's see how this all works out. I got a second here and a second there, so those go. I've got a meter cubed and a meter, that's a meter to the fourth, and that's a meter to the fourth. And so I've got Pascal. So we got it. That should all work out to be Pascals. Okay. Let's just go, let me get it on my calculator and see if I match what you guys get. So 100 there, divided by 100 cubed, getting a small number, times 1.5, times 10, divided by pi, divided by 0.01 to the fourth. Okay, and my calculator is giving me a really, really big number.
Where'd your 8 go?
Oh, great catch, whoever said that. Thank you. I'm missing the 8, so I'm just going to put that over here like that. Thank you so much, whoever said that. So I need to multiply this by 8. Okay, so let me pause for a second. I mean, the mechanics are what's important, but I would love it if we agreed on the answer here. Is that matching anyone out there?
Yes.
Thank you. Hey, what kind of units is that? Pascals. That's Pascals. Okay. And so is that a significant pressure drop? You bet you. If you were trying to pump glycerin, okay, through these 10 meters of pipe, the pressure here is going to be a lot higher than the pressure there. And you're going to need some sort of pump or something like that that pressurizes it. Okay, what is that like? Please don't write this down, but hopefully you remember what this fraction is representing. Let me just let you think about that. 14.7 over 101.3. Where are 14.7 and 101.3 in this course? Hey, well, you know, that went pretty well on test 1. A lot of you guys knew that atmospheric pressure is 101.3 kPa, and this is 14.7 psi. So I could use this fraction to convert this to this number from kPa to psi. So I'm going to divide that by 1,000. 382 kPa. Okay, so this this glycerin, as it goes from here to here, is losing about 55 psi. Losing about 55 psi. You can think about that as energy or pressure. Hey, we're going to need a big pump. We're going to need a magnum pump to do that. Okay. Hey, what if you're designing a system and you work on this and you figure out like, wow, that needs to be such a huge pump. What can I do about it? I still need this flow. What do you actually do? Well, hopefully it makes sense to you. Like the obvious thing to do is to say, well, maybe I could make the pipe bigger, because the bigger I make the pipe, okay, the more space the pipe has to flow and the less intense the friction is actually going to be. Hey, I didn't explain that very well, but it turns out it's an important idea that we're going to want to understand like a week and a half from now. Just to work that out though, why don't you see if you can come up with a slick way to say, look, what if we spring for a pipe that's twice as big? Can we reduce this number here at all? So the D equals 4 centimeters. Go ahead and give it a shot. And I'll be doing the number on the board. It basically is the same equation with just one number change there. One number change. Okay, so basically all I'm going to do in this equation is I'm going to take this radius and change it from 1 centimeter to 2 centimeters. So this is going to become 0.02 right here like this. That's going to become 0.02. All right, and I don't know if anyone's had a chance to check through it, but hopefully you can see we're dividing by a bigger number. So this number here should be smaller. And it should be instead of like 382,000, it should be like in the 90,000 order, something like 90,000. Let me try that myself, see how it turns out. And you can write, if you didn't get it yourself, you can write down the answer. But maybe if I could get verification. Actually, hang on just a second. Even better than that.
I'm getting like 23,000.
Yes, great job. Let me just try it myself. How about 23,873?
Yeah, same.
Ish. Okay. Wow, the pressure really, really dropped. It really, really dropped. And that's the pressure drop. And that's something that we're really going to notice, okay, and understand a lot more fully, that if you want to reduce pressure drop, make the pipe bigger and then the fluid fits more easily through the pipe. And as a consequence, you get less pressure. Okay, good. And that ends up being a huge choice. It's kind of in design. Do we want a big pipe so there's a small pump, or do we want a small pipe and therefore a big pump? Very interesting question to get through. Okay, hey, I'm just going to introduce the next topic and then we'll take our 5-minute break. And by the way, while I'm erasing or whatever else, stretch or ask me a question. Okay, we'll take our break in just a minute, but fluid flow indices. So let me talk about that really briefly. So that's it for chapter 6. There's a ton of material in chapter 6, but what we covered in class, that's what you're responsible for. This next topic is largely talked about in chapter 7, and that's fluid flow indices. And that's where we take a look at some sort of fluid and we do a computation of various parameters for that fluid. Maybe like we consider both its density and its viscosity and do some sort of computation with that. And that result gives us a feel for what's going on. Hey, just analogy really quickly. Here's an indice. Don't write this down. Here's an indice. BMI, okay? BMI. Hey, my doctor does that for me. He calculates my BMI. That's my body mass index, okay? And that's a calculation that does a combination of my weight and my height. And there's some sort of computation that's done with my weight and height, and you get the BMI, and that computation kind of gives a sense of what my health is like. what my health is like. What's my BMI? I want a lower BMI, but not too low. Well, that's the same thing for fluids. There are a bunch of different indices for fluids that you do a computation, and it tells you, gives you a sense of what the flow is going to be like. And we're going to only do two indices right now. One is called the Mach number, and one is called the Reynolds number. So before we get going on the, well, let me get the Mach number equation up there, and then we'll take our break. Fluid indices. The first one is called the Mach number. You've probably heard of that one. A very interesting idea. Okay, so the Mach number gives us for a flow. Okay, so for a flow. So let's say, I don't need to write this down. Let's say I have some sort of object and a fluid's flowing past it with a speed v. The Mach number for that situation is a comparison of this speed v versus the speed that a compression would flow in the fluid. Okay, so let me get that up there and then we'll take our break. All right, so very simple equation. Let me define those two terms and that'll be good enough, okay? So we're gonna do a comparison of V of the fluid, okay, is, by the way, the Mach number is usually used for a situation where there is flow of a fluid relative to an object. For example, if this were a flagpole or something like that, and then there was air flowing around it, we could calculate the Mach number. Or if this were an airplane here like this, okay, and it's flying along with a certain speed, okay, even if let's say it's going along at 600 miles per hour, okay, even if the air over here is stationary, we could say that this is analogous to the airplane being stationary and there being 600 mile per hour fluid speed relative to that. So basically V is speed of fluid relative to object. Okay, and C, I'll give you two definitions. C is the speed of a compression in that fluid or the way your book defines it is the speed of sound in that fluid. Okay, hey, so we're going to do a couple with examples with that very interesting idea. We've got some sort of flow around an object. What's the Mach number for our situation? And then once we get that Mach number, it's kind of like BMI. If my doctor does my BMI and he gets 31, he says, hey, Marcus, you got to cut out some stuff and get some more exercise. What if we get a Mach number of 7? What does that tell us? Okay, 5-minute break. We'll start again at 9:19. And I'm going to step out for just 1 minute. When I come back, though, please, if you have questions about what's going on in the course, material-wise or otherwise, please ask. All right. Well, first of all, just a little bit of conceptual stuff about that. What is this thing here? Speed of compression in a fluid. So that idea is really pretty simple. If I have some sort of fluid, okay, and I'm going to make it a gas, I wouldn't write this down, okay? And at some point within the fluid, I take maybe a couple plates and put them together so that I compress that fluid. That compression ends up moving. So what happens actually is if I push these plates together, I get a high pressure area right there like that relative to the surroundings, and that high pressure area ends up spreading and moving outward. So you get this compression area that moves out. Okay, demonstrating that. A couple ways you could demonstrate that to yourself at home, okay, is you could get a pan with some water in there like that, okay? And you could actually take some sort of, some sort of utensil and push down on that, and that's going to create a lot high pressure area right down there where you push down, where you actually end up pushing down. And then it turns out that that compression is going to spread out that way and that way like that. If you looked overhead at the fluid, you would end up getting a circle that goes out there like that. And we call that circle a compression. That compression actually ends up spreading out. Okay. Hey, another way actually to do this with a gas, by the way, these compressions travel through both liquids and gases. They even travel through solids. To do it with a gas, well, I can just do it really quickly myself. There's a gas right here like this, and I put my hands together. That creates a high pressure area right in between my hands, and that pressure travels outwards. When it hits our ear, we hear that as a clap. So compressions actually spread out and travel through fluids. Why would we be interested in the speed of a compression in a fluid? Well, again, no need to write this down. This just is giving you a little bit of intuition. Well, there's all sorts of flow situations where we get compressions. And a good example is an airplane. Okay, if an airplane's flying this way, okay, at its tip, it creates compressions, okay, which are high pressure area. Okay, would we like this plane to travel faster than this compression or slower than this compression? So that V represents the plane travel, and C would represent the speed of the compression. Okay, remember this is a high pressure area here, and if if we're trying to move, we don't like to encounter high pressure. So we would like it in a way if this was faster than that right there. So if this plane was going, say, 200 miles per hour, it would be great if this C was 400 miles per hour, because it would move away from the plane and you wouldn't be going into that high pressure. Okay, what if this was 400 miles per hour? Okay, well then the plane is moving right with that pressure, and at every point when it moves, the plane actually creates more pressure, creates this high compression, and so this pressure really builds up. And we would say in this case that the Mach number for this flight, again, just trying to give you some ideas, the Mach number is the speed of our object relative to the speed of the fluid relative to the object, or the object relative to the fluid. Those are the same things, it's a magnitude. So this over the speed actually of a compression in that fluid, and so this would be 400 over 400, and that number is 1. And so we would say that this plane is flying at Mach 1. And for people who are in the know in aerodynamics, they say, oh, if it's Mach 1, I can tell you some things about that, what's going to happen in this situation. Just like my doctor will tell me, look, hey, Marcus, if your BMI is 32, there's something that's going to happen to you. You're not going to be healthy later on. You need to make some changes. You guys go into aerospace, hey, it's Mach 1, you know what's going on. All right. What is speed of compression? That's a great way to think about it. The book says speed of sound. Well, sound is basically a series of compressions. If we have some sort of instrument, and I could represent an instrument by a tuning fork, when you hit that tuning fork, this tine right here vibrates back and forth like that. It's vibrating back and forth. And every time it moves this way, it creates a compression in that area right there. And that compression travels out. And those compressions travel at a certain speed. And we say that is the speed of sound. All right, hey, maybe that's enough about it. This is an easy equation, but it is helpful for understanding a lot of important phenomena out there in fluids. So let's just go ahead and do a quick example. Let me just put a reminder down here. I'm not going to ask you to memorize this, but 60 miles per hour is equal to 88 feet per second. So I just written that as a side. Okay. Bear with me for just a second. Okay. Let's say we have a plane. Okay. And it is going 800 miles per hour. Okay. What is the speed? What's the fluid it's going through? Well, it'll be going through air. What is the speed of sound in air? We could denote that as C air. Okay. And a good number, rough number for it is, bear with me for a second, I just had that on my calculator. 343 meters per second. So I'll just convert that. That's a good rough number, 344 meters per second into feet per second. Let's just do 1120 feet per second. What is the Mach number in that case? And then, hey, if you're an aerospace engineer, you're going to be able to say, hey, what's going to happen in a situation like that? By the way, this air over here is still air. So this is still air over here. Okay. I'm going to do a conversion over here and make this into feet per second. Okay, rounding off, I got 1.05. So I want to stop for a minute and see if that matches anyone out there, if there are any questions on that. I got 1.05. Okay. So 800 miles per hour, I got 1,173 feet per second. It's a little bit faster than the speed of sound in air. And it cranked out to be, so the Mach number is 1.05. How about units? It's unitless. And these indices, these fluid flow indices that we're going to work on that you work on when you do a lot of fluids, a lot of them are unitless. Kind of interesting idea, unitless parameter. Okay, hey, one more thing about it. If you're doing Mach number work, okay, this might come from your situation, like a plane's going 800 miles per hour. But how about C? How about the speed of sound? Well, you can look it up, okay? You could look it up, and this would be a very good estimate for the speed of sound in air. But it turns out the speed of sound depends on, for many fluids, it depends on temperature and other type relationships. So it turns out that it's useful to do a computation. And for homework number 7, I want you to be able to do a quick computation with the basic formula for speed of sound in gases. Let's get that up there, okay? So if we have some sort of gas, how fast is the compression going to move in that gas? Okay. So it turns out it depends on the temperature. And it's amazing to me that someone actually went through and cranked through this. It turns out it depends on the temperature, but the square root of the temperature. So if the temperature quadruples, the speed doubles. An interesting idea. It depends on a value that's in the table, and it depends on a value in the table. And you take the square root of all that. Okay. A little bit of practice, easy formula. The temperature is in absolute units.
Is that a K?
Yes, and we're going to take a look at that. That's in the same table as the R values in the table. So we're going to go to like table 1.6 or 1.7 or something like that to get those K values. And let's do that really quickly, okay? Let's figure out C for helium, okay, at an easy temperature. So let's say 70 degrees Fahrenheit. Okay, it's just plug and chug. Pull out your tables. This should be like money in the bank if it's on test 2, okay? hey, I can do this. I can work through it really quickly. First time through, take your time, find the values from the table, get the units from the table. Let's see if it all works out. I'm going to be doing it myself. So this is helium. What's the speed of sound in helium? Let's get it in feet per second, and then we'll talk about it a little bit later on. If you had a compression and it was going in for helium, how fast would it move? Please don't copy down what I have on the board. I've got one mistake up there. Or maybe more than one. I don't know if anyone sees a mistake up there, but let's let you think about it for just a second. So I was trying to do K. K is a value from the table. For helium, K is 1.66. It's something called the specific heat ratio. Thermo, don't worry about it for now. R, hey, we've done that before. That's the gas constant for our particular gas. 1.242 times 10 to the fourth, so I wrote it out. Okay, foot-pounds per slug Rankine. Temperature, there's a mistake. That's supposed to be in Rankine, so I should take 70, I should add 460, and I get 530 Rankine. Okay, so there we go. Let's finish that off. Let's finish that off, and please pipe up if you have a question or you see an error. I'm going to do the number, and then I'm going to do units. I got 3306. I believe that's right. Please, please pipe up if you see if there's a mistake. And then how about units? Well, obviously the Rankines go away. And now I've got a foot over a slug, and then I got a pound. You don't need to memorize this, but it can be incredibly helpful to remember that a pound is a slug foot per second squared. Slugs go away. I get foot squared per second squared. Underneath the radical, square root of that is foot per second. Okay. And hopefully you've seen this fact before. Sound travels a lot faster in helium than it does in air. So that's a lot bigger number there. Kind of interesting thing that the compression would travel faster in helium. All right, that is our first fluid flow indice. That is pretty important for ME120. What is really important for ME120 and the rest of your time here at Sac State is the Reynolds number. So that is our second parameter. So let's get that up there.
Professor, yeah. Professor, before you, where you have R, why'd you keep R in the equation? Yeah, right there. Why'd you keep R if
Gotcha. Good question. Let me explain that. That's a little bit confusing. It probably would be better if I had written it as degrees R. So the R in this unit right here is not this R as in the gas constant, but instead units for temperature.
Oh, got you.
Good question. Yeah, the book is a little bit better about that than me. They tend to do degrees R, and that makes less confusion. All right, good. All right, number two. Mach number. We want you to know the Mach number. Number 2, hey, what is the Reynolds number for flow? What is the Reynolds number for flow? You go on and you take heat transfer. Your professor's going to ask you, hey, you guys all remember the Reynolds number, right? You take thermal fluids, ME128. You guys all remember the Reynolds number. You do any sort of elective related to flow, you all remember the Reynolds number. So let's go over that really quickly. The Reynolds number is, once again, a fluid indice that you can think about as telling us the likelihood of turbulence. Maybe I'll just put it about, chance of turbulence. What probability or chance is there going to be turbulence in some sort of situation? And obviously it turns out that just like for the Mach number, if the Mach number for a flow situation is bigger than 1, we know our object is going faster than the speed of sound, some stuff's going to happen. If our flow is laminar, we have some idea what's going to go on with things like pressure and force, etc. If it's turbulent, where we get swirling flow and stream and bits of fluid crossing each other's path, we get different rules for pressure and for force. So it turns out that we would like to know, hey, what is the chance of turbulence, or what is the degree of turbulence? And that's what the Reynolds number is for. Okay, so just a very easy equation, but a little bit of intuition. RE is short for Reynolds number, REYNOLDS. So I should have, so let's see, when we're doing the Reynolds number, okay, I'd like you at least to think about this. What we're doing is what's called a comparison of, well, some books call it the separation forces to the cohesive forces in the situation. All right. Hey, if you write that down, that's good enough. The pictures I'm going to put up there, please just think about it. No need to stress about it a little bit. Stress about it or write them down. Okay. So situation like this. No need to write this down. Those represent pipe walls. We got super slow flow going in a pipe, super slow flow. Are we going to get separation between one arrow and the next arrow right next to it? Or are they going to just keep kind of flowing one right over the other? Well, if this flow is really, really slow, we're probably not going to get that, okay? But if we were to take this flow and speed it up and then create some sort of geometry, like something like this, okay? A sudden expansion. I'm going to make it even more sudden. Dramatic expansion like this. When this fluid moves along, it's suddenly going to, fluid nature abhors a vacuum. We're going to get some fluid suddenly moving here like this and some moving here like that. And if it's fast enough, this sort of disruption in the flow can lead to swirling type action. Okay. Another analogy where we could get separation forces. Going back to that rod that's on top of our car that is used for attaching a back rack. So let's just say our car is going this way like this. Relatively speaking, the air would be going that way like that. So we can imagine we have some air like this that's uniform flow. Okay. Another way of thinking about separation forces, I wouldn't write this down. I've heard some books, professors, et cetera, say, hey, separation forces are forces that would disrupt laminar flow. Okay, so we can think of there being layered flow over here. Would this rod disrupt laminar flow? Well, this line up here would probably just keep going, and this line right here would keep going. But this line right here, it needs to move down there like that, and this needs to move down as well. This needs to move up and over. This needs to move up and over. This here would almost stagnate and move here like that. Well, you can see you get all sorts of crowding in this area here like this. And all that crowding where that fluid's trying to fit into a small space can disrupt laminar flow. If we're trying to fit a lot of kilograms of fluid through a small space, it can be hard for it to maintain that nice laminar measure. So separation forces, one, it's going to depend on how fast the fluid's moving. In addition, it's going to depend on the density of the fluid, okay? If this were something if this were a fluid going like 10 feet per second, and in addition, it were also something like mercury, which is really dense, well, a really dense thing has to make some changes, and that makes it more likely that it's going to get away from laminarity or laminar flow. So separation forces, you might want to think about this or even write it down. Separation, so I'm going to call this A. Separation forces, it's going to depend on how fast the fluid's moving, or speed relative to our object. We figure out Reynolds numbers for flows that are interacting with objects, like an airplane, or a rod, or the interior of a pipe. Okay? It's also going to depend on the density of our fluid. The denser it is, the more disruption there would be, because there'd be a lot of mass in a certain area. Okay, and it's also going to depend on something about the geometry, okay, which your book uses as L, although L can stand for a variety of things. Okay, in this case right here, where I had that flow around a cylinder, okay, that flow around a cylinder, the relative length is going to be the diameter of the cylinder. The bigger the diameter it is, the more disruptive it is to laminar flow. So this is, I would maybe write this down, this L is sometimes called the characteristic length. Characteristic length for the flow situation. So those three things can possibly contribute to separation. If speed's big, if density's big, and if the length that's relevant to our flow is large, we can actually get disruption. Okay, B, what about the cohesive forces? Okay, what tends in that situation that I had earlier? Again, no need to write this down. I've got a sudden expansion, which will interrupt laminarity flow over here like this, okay? If that bit of fluid tends to go straight like that, what tends to keep this bit of fluid going straight in a layer on top of that, as opposed to going up and then separating and swirling? That's viscosity. So viscosity tends to keep fluids together and prevent turbulence. Okay, so some people were thinking, okay, is there some sort of calculation we can do to characterize turbulence? And it turns out the calculation is to combine these three things versus viscosity. So let me get the formula up there. I want to do it the same order as your book, so I need to pause for just a second. Yeah, your book does it as you take the density of the fluid, you take the speed of the fluid relative to the object, you take the characteristic length for the particular situation, okay, and then you divide by the viscosity. So this is actually, you know, if I had to give you a top 5 equations in fluids, that's on the list. That's top 5, the Reynolds number. Okay. Okay, well, let's just go ahead and do an example really quickly. Bear with me for just a second. That very crude drawing, that's, sorry about the drawing, that's supposed to be represent an airplane. And it's going through 88 feet per second through air, the standard air that we can get from the tables. Okay, what is the Reynolds number in that case? Well, we would need some sort of characteristic length, and we'll talk about that later on. But let's imagine the characteristic length that's used for a plate in this case, planing in this case, if we're wondering about, is it going to be turbulent flow here? If the fluid that is essentially flowing past the tip of the plane there, are we going to get turbulence in this region right here? The characteristic length might be the length from the top of the plane to the bottom. So this is a huge plane, 15 feet. Go for it, plug and chug. Get the Reynolds number, let's try to get the right number, let's try to get the units. Okay, there's my density. Need my speed. I need my characteristic length, which in this case is 15 feet. And I need my viscosity. Okay, keep going, you guys. Please, if any of those numbers don't look right to you, please let me know. I encourage you to pull out your calculator and just crank through the numbers and get a number here like this, and then somehow work out the units, because the units are important as well. Yeah, I'm really going to need a check from you guys on this.
That's what I got.
Yeah. Okay, cool. Huge number. By the way, Reynolds numbers tend to be pretty large sometimes. So the Mach number, a lot of times we're doing like Mach 1 or Mach 0.5 or Mach 2 or things like that. Reynolds numbers can be really large. Okay, second thing, how do the units work out? I'm going to get going on that. I'm going to do some work on the side, all right, to work out the units. I'm going to erase my formula. Erase my formula. Slug per second, foot per second, foot, and then I'm going to invert the denominator, foot squared per pound second. Wow, that is a ton of stuff. I think what I'm going to try to do is see if I can find a pound in here, recalling that a pound is a slug foot per second squared. A slug foot per second squared. And that's kind of interesting, actually. If we get the density times the speed, we get that. Because if I do the density times the speed, yeah. Something weird's kind of going on. I'm sorry, guys. Let me think for just a second. Pound, pound. Hey, you guys, I'm sorry. I'm not sure what I'm doing wrong. I'm going to stare at it for another minute. Turns out all the units are supposed to cancel out if we do this correctly. Oh, my density units are way off. 2.38 times 10 to the negative third. Check out my units. I totally screwed up. This is slugs per foot cubed. I'm so sorry about that. Glad at least I caught myself. Okay, so I should put foot cubed here. I'm going to erase that black bubble. Erase that black bubble. I'm still looking for a pound. Okay, so a pound would be a slug foot per second squared. Slug foot per second squared. So I think we got it. Let me try it again myself. Slug foot second. So all this stuff here, this plus this plus this plus this is a pound. So, and then there's a pound down here like that. So all that stuff cancels with the pound. And now let's see what we're left with. Foot cubed in the denominator, foot cubed here. It's foot cubed for foot cubed, so it's unitless. So just like the Mach number, the Reynolds number is unitless. Okay. What do you do then? Okay, what do you do once you calculate this Reynolds number? Well, you know then for a situation, after a while, you'll develop a little bit of knowledge or charts you can go to and say, hey, for this situation then, this scenario, like a plane, this Reynolds number means either turbulent or laminar. And we're gonna work our way to this. I hope it makes sense to you guys. This plane is going really, really fast, 600 miles per hour. It's probably true that this flow at the nose area is gonna be turbulent, and this number would indicate it's turbulent. Okay, one more, probably the primary case for the rest of the semester. We're going to calculate Reynolds numbers in many situations, but one of the key calculations for mechanical engineers is doing the Reynolds numbers for pipe. So before we do the example, let's get the equation up there, and I'll put it down below so we can we can refer to it as we're doing the example. For pipe flow, once again, so we got a pipe here like this. Again, we got a fluid going through the pipe. Is it going to be nice layered flow, which works out pretty well for pumping and things like that? Or is it going to be turbulent flow where we have fluids swirling and some fluids crossing lines, etc.? Okay, well, the more speed is going to make a difference. The faster the fluid's going to go, the more likely it is turbulent. Okay, density is going to make a difference. The denser it is, the more fluid we're trying to squeeze through that pipe. Viscosity is going to prevent turbulence, and the relative distance, the relative number is the diameter. Okay, so D stands for the diameter. So you might want to write that down. Hey, famous Reynolds numbers. Okay, famous Reynolds numbers, just like Mach 1 is a famous Mach number. Okay, for pipe flow, if the Reynolds number is less than 2,100, okay, Reynolds number is less than 2,100, the flow within the pipe is laminar. Doesn't matter what the fluid is, if it's glycerin or mercury, etc. Okay, and then if the Reynolds number is larger than 4,000, that's what your book uses. I've seen different numbers in industry. Then we get the flow is turbulent. Okay, we're going to do a lot more with pipes, but that's a good starting point. So you might want to write that down. By the way, this material we're going over right now, not on homework number 7, not on quiz 2, pardon me. All right, let's get you going and imagine you're an engineer doing some very, very practical design. Okay, so let's say we got some water. We got the situation where we want to move water from over here to over here like that, and we're going to size pipe. We want to move 74.8 gallons per minute, and I'll explain why I chose 74.8 in just a little bit. Okay, and it's H2O, and we're supposed to figure out the diameter of our pipe so we get laminar flow. And we're going to be a bit conservative. If our Reynolds number was 2,000, we're good to go. But we're going to be a bit conservative, and we're going to take that Reynolds number down to 1,600. Okay, go for it. plug and chug, going through and solving for diameter. Please feel free to speak up if you're not quite sure what to do. I'll be doing it on the board in just a minute, but I'd like you to see if you can get going and get that sized. Oh, actually, I should hesitate for just a second. So by the way, this is what I'm going to do at some point in this problem is I'm going to figure out the diameter by doing the Reynolds number times the viscosity over the density times the speed. Okay, but clearly I don't have the speed. What is GPM? It's Q, it's flow. So I'm going to have to somehow go from Q to speed. And so this is the work I'm going to do. I'm going to erase it really quickly. Okay, so just a quick reminder. We can get flow for a fluid going through some sort of passageway by doing average speed times cross-sectional area. Average speed, that's important here. The flow in the middle would be going faster than the flow at the edge, but we're just going to use the average speed in this equation. And in the Reynolds number, this speed is the average speed of the fluid for pipe flow. Okay, so the V is we should solve for the speed by doing the Q divided by the area. We would like this to be feet squared per second. 1 cubic foot is 7.48 gallons. A number I'm not going to require you to memorize, but it's good to know. So this should be 10 cubic feet per minute. And we would like to put this in per second. So the Q is 10 cubic feet per minute. And if you think about it, there's 60 seconds in a minute. So this would be 1/6 cubic foot per second. And then we need to divide by the area. So before we finish this off, let's sort of agree about how fast that fluid is moving. Good computation, fluid speed, something that's worked out all the time with pipe flow. Oh my goodness, I've really messed up on this. Hey, this is all really good, but we don't know the diameter. That's what we need to solve for. So I'm sorry. What I'm doing is good, but I need to do a little bit more work. So let's see, the area is pi d squared over 4. There we go. The area is pi d squared over 4. Now I can go to the Reynolds number. Really sorry about that, you guys. So here's the first 2 steps. And now I'm going to go to the Reynolds number equation, solve this for V. Okay. Pardon me, solve this for D. So Reynolds number for the pipe. So here's the equation I'm going to fill in and see if I can make sense of it. Reynolds number for the pipe is 1600. And that's going to be equal to the density of water times the speed of water, which is all this stuff right here. 1/6 over pi d squared over 4. The 4 would go up to the numerator. So 4/6 is 2/3. So I would have 2/3 over pi d squared. Okay, so this is speed, and then I would multiply by the diameter, okay, and then I would divide by the viscosity. Whew. Sorry about that, guys. Let me pause for just a second and see if that all makes sense. I'm going to erase this stuff here. Okay, so what am I trying to do in this case? I'm trying to solve for diameter. I might want to do a little bit of simplifying on this complex looking fraction. So there's going to be a rho in the numerator. This 2 is in the numerator. okay? That might be it for the numerator. In the denominator, there's going to be a pi, and there's going to be a 3 pi, okay? There's going to be a viscosity, okay? And then this is d squared, and this is d here, and this d squared in the denominator, so there'll be a d like that. So that's the algebra. 1600 is equal to 2 rho over 3 pi mu d, and then I need to do some algebra and get d by itself, and I'll try that myself. Okay, let's just crank through that and see how that turns out. See how that turns out numerically. Good. And so the density we'll get from the tables, and the viscosity we'll get from the tables. Okay, I believe I got those numbers right. Let's just crank through on our calculator and see if we can agree on a number. Two times 1.94 divided by 3 divided by 1600, getting really, really small, divided by pi, getting really small, divided by 2.34, and then divided by 10 to the negative fifth. Okay, my calculator is giving me about 11 when I go through that. I'll see if anyone else got something like that.
I got that too.
Okay, wow. By the way, if I had more time, I want to get going. The unit, we would show you how the units work out. The units turn out to be feet. Oh my goodness. If I wanted to get this flow here, and I wanted the pipe to be laminar, I need a huge pipe to do that. And that in general turns out to be true with water. It's hard to get water to be laminar flow, which may not seem right to us, but if you ever look at some sort of channel, okay, with water flowing at a non-trivial speed through there, you get swirling pretty easily with water. An example is actually when water comes out of a pipe and you can see the flow coming out. That flow sometimes is not really, really smooth. There's some swirling within that flow. Water is really, really hard to get laminar because of its nature. Okay, hey, so sorry about that. I got a little bit off track going through it, but that's a really, really good challenge. Sizing pipe for either laminar or turbulent flow. We'll give you practice on that on homework number 8.
Question?
Okay. Yes, please.
I just don't know where you got the 1.6 feet cube per second when you're trying to.
Okay, sure, absolutely. Right up here, this thing right here.
Yeah, I just don't know where you.
Okay, so by the way, please don't stress about it. Ordinarily, we would probably give you the flow in these units. But I gave you this flow, 74.8 gallons per minute, and I'll put the numbers up there. 74.8 gallons. It turns out that there is, for every cubic foot, has 7.48 gallons, which should be a pretty surprising thing. But if you got a foot cubed of a box that's a foot cubed, it would contain 7.5 gallons. So that is actually then, if you do the math here, you get 10 cubic feet of water per second. So that's just doing this math right here, per minute, okay? And then we want to fill it in cubic feet per second. So a minute is 60 seconds.
Oh, got you.
So then 10 over 60 turns out to be 1/6.
Got you. Okay. I just
Good
didn't see
question.
it.
All right. Hey, we're almost done for today, so we're going to work for another 16 minutes or so. Couple more couple more topics for today. Probably the number one though is we really, for this last bit of lecture, is we really want you to be able to do computations with the Reynolds number and give you a sense of what it's telling you. It's telling you, you could say like degree of turbulence or likelihood of turbulence, etc. Okay, so this next topic relates to the Reynolds number, and it's a new fluid property. So some properties that we have for fluids are density, okay? We got viscosity, okay? We've got C, which now you know what C stands for in ME120. C is the speed of a compression in a fluid. So we could speak of the speed of compression in helium or the speed of compression in glycerin, etc. Pretty interesting that people have figured that out. And this next property is a Greek symbol that looks like a lot like a V, but it's kind of like it comes almost straight down over here and then has a little bit of a curve like that, almost like you're doing a bit of a sine wave, and it's called a nu. Please don't worry about making this beautiful, but I want you to recognize that it's actually not a V, it's a Greek letter nu. And this is the symbol for what's called kinematic viscosity. So let's talk about that really quickly. So nu, kinematic viscosity. Okay. All right. Here, the book doesn't do this, but some other books I've seen have done this. They basically, what they do, basically a great way to think about this kinematic viscosity, it could be thought about a fluid resistance to turbulence. All right. I'm not going to test you on that. Okay. I'm not going to test you on that, but you might have if you say this to another professor, they might say, that's kind of weird. Or some might be pretty impressed. They say, oh, that's right. That's really what kinematic viscosity is measuring. So please don't write this down, but let's take a look at a situation, okay? I've got some sort of object that's standing in the way of a fluid. I like that idea of the rod on top of our car, which holds our bike racks. As we're driving down the highway, is this flow over this rod going to be turbulent, or is it going to be nice and smooth? Well, some depends on how fast the rod is moving, right? If I'm speeding and going 80 miles per hour, it's a lot more likely that this could be turbulent than if I'm just putting along slowly at 10 miles per hour or something like that. Okay, but what about the fluid itself? To what extent is the fluid going to be is the resistance to turbulence going to depend on the fluid type? Well, here's one factor to write down, again, not thinking about. What about the fluid viscosity? Okay? If the fluid is more viscous, is it more or less likely it's going to be turbulent? And viscosity is the idea that this fluid kind of coheres together. So this bit of fluid here might kind of go around here like this, and is this fluid going to cross it, or is it going to kind of just move smoothly with it? Well, the more viscous the fluid is, the more likely we get this smooth layered pattern like that. Okay, another factor is density, about the density of the fluid. Okay, well, a great way, at least I think, to think about this is that if we think, are we going to get turbulence, okay, with this fluid that's coming here like this bit's going to keep going straight, okay? But in this region right here, we've got to fit some fluid through in that circle I just drew. And we got to fit a lot of fluid through this area because it's got to go up and go through this little bit of passageway. Well, the denser the fluid is, the more we got to fit through this small area. And as a consequence, well, hopefully you remember that when we have pipes and we go through a narrowing section, I think you guys are all getting used to the ideas that we're going through a narrowing section, that fluid speeds up. So the denser the fluid is, the more possible kind of speed up and other effects we have. So the more likely it's fluid that we're going to get turbulence. So if viscosity goes up, a fluid has more resistance to turbulence. As density goes up, we have less resistance to turbulence. And so what some fluid people do is say, look, I can take mu over rho, and that's going to tell us how resistant the fluid is to turbulence. And so let's get that up there, okay? You don't need to know that mu over rho is resistance to fluid, resistance to turbulence, but you need to know this definition. The kinematic viscosity of a fluid is mu over rho. All right, let's get at it. What I would like to do is work together with you guys and see if we can get as many of these up on the board in the last few minutes. Okay. Okay, hey, let's do it in SI. And let's go ahead and do 3. That'll be good enough for this topic. And let's do glycerin. You guys do glycerin. I'll do mercury. You guys do water. And you guys do helium. Look, just write down plug and chug. Just write down plug and chug. Please don't stress about this. We'll get the numbers on the board and see if we agree. Don't need to write any units in this chart. We'll talk about the units later on. Just go to the tables and pull those numbers up. Remember, we're doing SI. We're doing SI. Oftentimes, kinematic viscosity is written in scientific notation. So there's your first line. Viscosity 1.5. Glycerin's incredibly viscous. Hey, it's pretty dense. It's denser than water. If I do mu over rho, I get 1.19 times 10 to the negative third. All right, try to keep going. I'm going to do mercury. You guys do water. And if you get it done, do helium. Again, we're doing SI. Okay, hey, let me talk about these numbers with you real quickly. So first of all, among the 3 that I have on the board so far, glycerin is the most viscous, and it's probably that it's the least likely to be turbulent. It has the most resistance to turbulence. And among the 3 numbers here, this is the biggest number by far. By the way, what kind of units? Well, you can go through the calculations yourself, and the units for kinematic viscosity turn out to be quite simple. They're meters squared per second. So you might want to write that down here. They're meters squared per second. If we had time, I would get those units for you. Okay, third thing. These numbers are actually in the book. There's a kinematic viscosity column. And that's going to be true for almost every fluids book that you do. You might think, okay, I need to calculate kinematic viscosity, but oftentimes it's given. It's such a useful parameter that it oftentimes is given. Okay, real quickly, let's go through the others. Mercury. What if I try to squeeze some mercury through a passageway? Is it going to be turbulent? Okay, it doesn't need to be a passageway. It could be around a cylinder or something like that. Hey, it's not very viscous compared to that. It's really, really dense. So for those two reasons, it has very poor resistance to turbulence, and you get 1.15 times 10 to the -7. So mercury, if it's flowing, is really likely to be turbulent. It's kind of interesting. Okay, how about water? Where does it fall on the scale? Okay, well, its viscosity is really similar to that to mercury, but is much, much, much less dense. So as a consequence, this number right here is bigger than that number there. And water has more resistance to turbulence than mercury. How about compared to glycerin? Well, this is a very small number compared to glycerin. So water is more likely to be turbulent than glycerin. Okay, hey, let's do the last one, helium. I'm just going to pull the numbers from the table. What about the viscosity of the helium? I bet that helium's resistance to shear is incredibly low. So let me get that up there. And by the way, if any of my numbers look wrong, please let me know. I get for helium 1.94 times 10 to the -5. Helium has virtually no resistance to shear. Okay. How about its density? Well, helium at standard temperatures is very low in density, and it's 0.166. 0.166 kilograms per meter cubed. So if I have some flow of helium, a certain, say, volume flow rate coming in, there's not a lot of molecules that need to fit into that space. So as a consequence, compared to water, what about its resistance to turbulence? It is 1.15 times 10 to the -4. And bear with me for a second. I just want to check that I got that right. 1.15 times 10 to the -4. Yep. So helium is less likely to be turbulent than water or mercury. Usually we think of gases as pretty easily becoming turbulent, but man, water becomes turbulent very, very easily. Okay, last equation of the day then. So we're going to combine the two equations that we just did. So in general, okay, we have some flow approaching a passageway. You need to write this down, or maybe approaching an object, like a plane or something like that, or a car or something like that. Hey, is the flow going to be turbulent? We do the Reynolds number calculation. We take the density of the fluid, the speed of the fluid relative to our object. We take some sort of characteristic length that we learn about, and we're going to be doing that during the rest of the semester, and we divide it by the viscosity, okay? And this gives us an idea about what sort of parameters cause separation versus what keeps coherent laminar flow. Hey, if kinematic viscosity is mu over rho, we don't need all four parameters. We could do this calculation a lot more quickly, because I could take this rho and put it down here like this, and I would have that the Reynolds number is speed times characteristic length divided by mu over rho. And that's kinematic viscosity. So another way of doing the Reynolds number is BOL, kinematic viscosity. So both these are good equations. And which one do you use? A lot of time it depends on the information given or how fast you want to work. And we got 2 minutes left, so let's see if we can do an example really quickly where we use this second formula. We're going to make this easy. We got a smaller plane, still a big plane. The height of its nose area is 12 feet. This height is the characteristic length for this situation. It's going 880 feet per second. Go, let's figure out the Reynolds number. Number in units. We can do it in 1 minute, particularly if we use this equation because it's faster. Go for it. By the way, I'm just assuming standard air, not air at altitude, et cetera. We'll hopefully talk about that another day. I'll be done in just a second. I understand if any of you guys need to sign off. It is actually 10:20, so please feel free to sign off if you need to get out of here. Huge number, 6726, 1147. And how about units? Ah, beautiful. Foot squared per second, unitless. Would that flow be turbulent? Hey, once you do a little bit more with aerospace type stuff, you come up with guidelines for transition to turbulence. The answer is yes. Hey, I kept you guys a minute late. I apologize. That is it. I will stay for 5 minutes and see if anyone has any quick questions. I will post solutions to homework number 7 early this afternoon, and I will have office hours this evening. So that is it. Thank you, everyone.
Quick question, Professor.
Yeah.
When you were looking at the kinematic velocity, viscosity of air, what was the main reason you chose to use the BG units instead of the SI units for this equation?
Ah, very good. It just came from the fact that the given information here, if you take a look at the problem on the board, the speed with the V term was given in feet per second.
Oh, you just looked at that and
yes, and that means it's going to be easier for you. So when you're deciding whether you want to do SI or BG values for fluid parameters, take a look at the givens on the problem, and usually there'll be a choice that makes the computation easier.
Okay, got you.
Good question.
That was just my main question. I just want to know why you.
No, good question. Good question.
Okay, thanks, Professor. And you said you have office later on today?
Yeah, I will send out it'll likely be early this evening, maybe like around 7:30. I'll send out a Zoom invitation, okay?
I appreciate it.
Absolutely.
All right.
Hello, Professor.
Yeah.
Hi, how are you?
I'm good. I'm doing pretty well. How are you doing?
Good, good. I want to talk to you about my test 1 grade.
Okay. And who is this?
I'm Mohammed.
Mohammed. Yeah. Let me just make sure. I want to make sure it's private. If I would feel you might feel more comfortable with private. Let me see how many other people are on here. Give me just a second.
Okay.
Hey, it's just you and me. So go ahead, please.
Yeah, Professor. What's the problem? Which one is the one you don't understand?
Sure. Well, in the email, did you see I talked about the ideal gas law problem?
Yeah. Is that 5, problem 5, section C?
Perfect. That's exactly right.
So which one? What number?
Okay. So if you read the email said that for the gas constant, you use something that wasn't in the tables and wasn't part of the course. So do you know what I mean by the gas constant?
Yeah, that's right. Yeah, for this, we used to, because I did not take physics and chemistry here in the United States. So
Okay.
we studied that back home,
Okay.
like, and also like different language. And
Sure.
like we're not allowed to use the tables back there. So like for me myself, I memorized like the main like the air,
Okay.
oxygen, and hydrogen. We used to use that a lot of the time. So
Okay.
I kind of memorize it.
So let's see. What you did was you used two numbers. You had an R
Yeah,
of,
the universal gas constant.
yes.
Yeah, that's what we use all the time because
Okay.
it's memorizable. And the molar mass of oxygen is
Got
like
it.
we
Okay.
used to do a lot of problems back there.
Okay. Mohammed, that makes sense to me. I needed to check though.
Okay.
And so if I could explain where I'm coming from, I don't know if you can see the board right here, but for many problems in class and on homework, we use this equation right here.
Right.
And on homework and in class, we got this R value from the tables that are in our textbook. So I'm not saying you did it wrong, but can you understand that that's what I was looking for?
That's right. And I had the table at that day, but if like I was doing it fast and like I kind of
That's
nervous
fine.
with the exam. I
That's
did
fine.
like A314 like over 322 because I know the molar mass of
Got it.
oxygen.
That's fine. So and so I appreciate that, Mohammed. That makes sense to me. That makes sense to me. If you could just understand where I'm coming from, you know, I'm having
right.
some issues with this online testing. I'm doing the best I can.
Sure.
I'm having some issues where it's obvious that students went to the internet even though they're not supposed to.
Yeah, that's true.
So you could see how someone would go to the problem said use the ideal gas law, and you could see how someone could go to the internet and say, oh, you use 8314 and then you use the molar mass for the particular gas and take it from there. I'm not saying that I thought that you did that, but I felt like I had to check with you. I would check with any student about that. You know, in addition, I have some issues I've had, not this semester, I'm not sure about it, but I've had some issues in the past semester where like there's some things happened where, you know, like a student has set up a camera that records their writing, and then for a buddy has the camera transmit to their buddy what they're writing so that the buddy can just write stuff down. So when stuff comes up where there's some sort of very unusual computation on a paper that is different than the way we learned it in class, I need to check. If there are two students' work that is virtually identical line per line, including some very strange things that ordinary other people do, I need to check. So I wasn't accusing you of anything, but I needed to check.
I understand, Professor. Yeah,
Okay.
like those gases, oxygen, air, hydrogen, we used to do a lot of time. So I kind of memorize it.
Mohammed, that makes sense to me. I gotcha. I will update the spreadsheet and expose, and you'll be able to see your score. Okay.
Awesome, Professor. I appreciate it.
All right, Mohammed.
I'll see you tomorrow.
Take care.
Thank you.